Good day, everyone. I am Jin Zhang Liu from National Zhongzheng University, Taiwan. Today we will present our paper entitled Unsupervised Video Anomaly Detection Using Memory-augmented Deep Neural Net. This is the outline of our presentation. First, we will give a brief introduction. Then we will describe our proposed approach. Then we will show some experimental results, followed by concluding remark. For environment safety, cameras are usually installed in different living environments to monitoring different activity and prevent emergency. Three difficulties of video anomaly detection. The definition of anomaly is vague. Second, data imbalance between normal and abnormal sample, and high deviation in abnormal samples. Most existing anomaly detection approaches are unsupervised learning-based approach. Two main categories of video anomaly detection approaches: handcraft feature-based and deep learning-based. For handcraft feature-based approach, handcraft spatial temporal transform and spatial temporal features are extracted and employed to perform video anomaly detection. For different deep learning-based approach, various deep neural net are employed to perform video anomaly detection. In this study, an unsupervised video anomaly detection approach using memory-augmented deep neural net is proposed. Figure 1 shows the framework of the proposed approach. Figure 2 shows the proposed encoder-decoder architecture with skip connections. The first part is encoder, the later part is decoder. For encoder, as shown in Figure 2, to get more temporal information for consecutive video frames are fed into encoder. And each video frame will normalize, and all pixel values are normalized to the range -1 to 1. The first layer of the encoder, the proposed inception module and a script and the excitation block are added. Each remaining layer contains a direct convolution, batch normalization (BN), and liquid rectify linear unit liquid review. To extract more low-level features, as shown in Figure 3, a modified inception module with BN and the liquid review is employed in this study, in which BN batch normalization is employed to cope with internal covariance shift. In this study, two activation functions are employed. Sigma, a linear activation function, is employed and defined as equation 1. Liquid review employed in the encoder and the decoder is defined as equation 2. To learn the correlation among channel-wise feature map and automatically extract important features of different feature maps, the proposed inception module will be followed by a script and the excitation block shown in Figure 4. The output feature of normal and abnormal feature frame at the encoder may be replaced by normal feature in memory module, so that feature video frame predicted by the encoder are only normal event. The error between the predict abnormal and the ground truth video frames will greatly be increased, so that we can determine whether input video frames are abnormal. The output of a proposed encoder will be denoted as Qt. As shown in Figure 5, Qt is divided into n small query, and the memory module considers n memory item, and each memory item will contain the features of a normal event. Figure 6 and 7 will show the memory module consists of two parts: memory reading replacing part and the memory updating part. Figure 5 shows the proposed memory reading and replacing architectures. Figure 6 shows the process using Qt and P1 through PM to generate a new small query. Figure 7 shows the process using PI and Qt1 through Qtn to generate a new memory item. As shown in Figure 6, using the memory reading and replacing architecture, all Qtn are replaced by feature of normal event by attention-based memory addressing. After concatenation of all Qtn, Qt is absent. Qt head is absent, replacing the original Qt. So the new Qt head is fit into the decoder for video frame prediction. For memory updating, to increase the diversity of memory item and read memory item efficiently, as shown in Figure 7, the memory module will be constantly updated during the training stage. For the decoder, as shown in Figure 1, to predict video frame, decoder 1 learns the appearing information on normal event, called appearing decoder, whereas to estimate optical flow, decoder 2 learns object motion between consecutive video frames, called motion decoder. Here, decoder 1 and 2 has a similar network structure containing general convolution transporter, convolution BN, and the liquid review. Transport convolution is a type of upsampling. In this study, total loss function for training will contain four types of loss, namely feature similarity loss, feature separation loss, appearing loss, and motion loss, which is computed as equation 4. In this study, to pick signal to noise ratio, PSNR, APP, and PSNR, MO, respectively, are computed, and the anomaly score of the teeth input video frame, IT, is computed as equation 5. Finally, based on threshold, the teeth input video frame is determined as normal or abnormal as equation 6. In this study, resolution of input video frame will be normalized, resizing, and all pixel values are normalized to range -1 to 1. And the ATOM optimizer is employed in this study for training and computing. This shows the system setup. We will use 3 datasets: CUHK Avenue, UCSD, PED2, and Shanghai Tech. 2 objective metrics: AUC and EER are employed. In terms of AUC and EER, performance comparison between 17 comparison approach and the proposed approach on CUHK Avenue dataset are listed in Table 1. Similarly, performance comparison between 17 comparison approach and the proposed approach on UCSD dataset are listed in Table 2. Performance comparison between 17 comparison approach and the proposed approach on Shanghai Tech dataset are listed in Table 3. Figure 8 shows some illustrated location of abnormal event on CUHK Avenue dataset. Figure 9 shows some illustrate location of abnormal event in UCSD dataset. Figure 10 shows some illustrate location of abnormal event in Shanghai Tech dataset. Concluding remark. In this study, an unsupervised video anomaly detection approach using memory-augmented deep neural net is proposed. Based on the experimental result best obtained in this study, in terms of two objective performance metrics, namely AUC and EER, the overall performance of the proposed approach is better than those of 17 comparison approach. Thank you for your attention. Thank you.